Okay, hello, and this is the fourth of my 5 videos about the 5 physics articles I found online. So, let's get to it. This one is called Quantum Darwinism, an idea to explain objective reality passes first tests. So, this article surrounds the topic of a new theory explaining quantum mechanics, or a new theory explaining part of quantum mechanics called quantum Darwinism. So, before the article, it launched into an explanation of basic quantum mechanics, which I think I'll probably reproduce here because quantum mechanics is something that I learned as I was reading through this via searching up a lot online. And for anyone else who is not Mr. Hameli watching this video, it would be hard to understand. So, quantum physics has a reputation for being confusing and counterintuitive. When looking at atoms and subatomic particles, the predictability of classical physics dissolves into superprobability and statistics rather than being definite. So if I were to look at a phone on my desk, it's it's just there. It's certain that it's there. If I walk away for an hour, it's going to be there when I come back. Whereas if I were to look at an electron, that is not the case. It could be in multiple places if I turn around and go back, or if I had to look at it and then blink. So the question becomes, how does this quantum uncertainty transform into the consistent, definite world of classical physics that we know? So uh, how does our world relate to quantum physics? Because this phone, for example, or I am made completely of atoms and electrons and subatomic particles. So how does that soup of probability eventually transform into the definite world of normal classical physics that we know of today? And that is what quantum Darwinism attempts to explain, how quantum physics transforms into classical physics over time. Yeah, how it just transforms into classical physics. So this transfer from quantum to classical is sometimes called the quantum classical transition. I'm going to write it down over here. So the quantum classical transition. And it is important as this is what quantum Darwinism focuses around. So, however, there's no reason to think that large objects and small objects are governed by different basic principles. Like, quantum physics still governs me because I'm made of subatomic particles. It's just when we get into large clumps of these subatomic particles, it seems that the way they interact seems differently from a huge scale. And as physicists gain knowledge, there comes a greater understanding of how quantum mechanics becomes classical through particle interactions with one another in their environment. So one such theory explaining this transformation is enter quantum Darwinism. And it's the idea that objects' physical properties such as position or speed are taken from a menu of quantum possibilities deemed most fit through a loose natural selection process. The most fit possibilities appear the most, therefore determining the physical properties that observers see. So quantum physics, quantum mechanics doesn't have these set properties like mass or well, yes, mass is a set property, but set properties such as position. A particle can be in multiple states at once. So say this little red dot here is my particle. A particle can be here, 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 and over here as well, all at once. It could even be across the universe over here, all at once in quantum mechanics. But that is not the case in classical physics. If you set a pencil down, it's going to be there when you come back, as long as no force is applied to it. Or say velocity. With velocity, when a ball is kicked, it goes, say, 10 miles an hour, and that's that. But in quantum physics, velocity is all relative, and velocity really can change at a time, since the objects are in so many different places at once, here, 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 possibilities, then velocity doesn't matter if it's in all these places at once before it is observed. So, although there's some flaws, this quantum Darwinism helps try and reconcile the rift between quantum physics and the way we experience things in regular world physics, the classical physics we know of. And although it looks pretty nice on paper, only recently has the theory been tested. So 3 independent research groups in Italy, China, and Germany have searched for clues of this natural selection process. And although the tests are pretty rudimentary, it seems that from what data these 3 teams have gathered, it all checks out. It all works. So let's move over here. I'm going to delete this guy over here. And we're going to get ourselves a blank screen. So at the heart of quantum physics, or quantum Darwinism, is the concept of measurement, and measurement is at the heart of all quantum mechanics in general, or making an observation. In classical physics, when we make a measurement or we are recording one, there's only one state of an object. So, say I have a ball, a blue ball, sitting right here, that's a black ball. Let's try blue. A blue ball sitting right here, and it is sitting at position, let's call this x of 10, y of 15. And I kick said blue ball, and it moves over here at a rate of 5 units per second. And it is now at x of 15, y of 15. Well, that happened, and only one thing happened. If I were to turn around, say here, and then stop time, turn back around, and look at it, well, the ball is here. There's only one spot. It is here, for a definite sure. But when working with quantum physics, a measurement simply shows us one possible state of the object, in which that state was chosen from a range of probabilities, and that one state is what we see. So if we move over here, or I'll just draw it down here. So let's call this quantum physics. Let's say we have a particle. Let's call this a free roaming electron right here. This electron is in a field that is surrounding a proton. And when we measure for said electron, we find the electron over here. But that doesn't mean that it was there before we measured it. It could have been over here, or over here, or over here, or over there, or over there at the same time. So then say we try and do another measurement, and the electron is all the way over here when we measure it again. So even if we were to stop time, turn around, look at it again, it's not in the same place. It jumps around constantly, and it's only until we measure it is when we see one possible position picked out from a range of possible positions. It's not like regular physics, in which we see a ball and we see it, and that's just, it's there because it's there. That's not the case with quantum physics. It's there because since we can't see the superposition, it had to collapse into one state for us to see it. So this range of probabilities that exists is the superposition, as I've said, and the state the object is in before we measure it. Once measured, the range collapses into only one state of the superposition, what we see. And the reason we can't see the superposition is because an observation creates an interaction between the observed thing and say an electron and the measurement device, or just the world around it in general. So say we have an electron in a superposition over here, and right now it is in multiple states at once. So, I'll try to erase that here. It's in multiple states at once. So this is what we will observe it in, but it can be in all these states over here. Well, when we've measured it, this electron has been affected by the outside world. So say a photon comes in and smacks it. Well, in the quantum world, it's not hit technically, because before an electron moves from the quantum area into our regular physics realm where it becomes a point, it behaves more like a wave. It's a wave of all the possible probabilities that the electron can be in. The wave covering all these possibilities. And only when we observe it or look at it does it collapse into the one point like the electron. And this holds true for any object, any quantum object. So this photon here that just hit this electron is also like a wave. It has a range of possible things. Well, when they interact with each other, these waves cross. They've now become entangled. So that when one is changed, since these waves have now become synchronized with each other, when one of these waves is changed, the other wave has changed, therefore changing where the electron would be and where the proton would be, what the speed of both would be, how fast what their polarity would be. And this, as I've said, is called entanglement. The quantum states have now been inseparably changed by their collision of each other. So when one collapses into a single state, the other does. The process in which quantumness disappears, it is called diffusion, and let me restate that. The process in which quantumness disappears due to diffusion in the environment is called decoherence. Since there's a bunch of different, say, photons hitting this particle, and then maybe there's other air molecules sitting around that are hitting this particle as well. This is an air molecule with its waves. They're all getting jumbled together. All of these waves are getting thrown together. So the moment that these collapse, when one of these collapses, all the rest of these collapse as well, which is the reason we cannot see this superposition of the single proton, or the single electron. It's because it's been interacted with by all these other particles. It's changed somehow, and when one collapses, everything collapses, and it collapses at a ridiculous rate. A rate so fast that we can't even begin to process it. So that is why we cannot see the superposition. So this decoherence I'm talking about is important to the quantum classical transition, as it explains why quantum behavior is hard to see in large systems. So talking about the speed at which this decoherence happens, it takes about 10 to the negative 31 seconds for it to happen, which is Planck time. This Planck time is the time it takes for a quantum wave to collapse into one state. So this is happening at a ridiculous amount of times per second, so fast that we can't comprehend it. So it's not possible to say that decoherence alone makes quantum behavior to appear classical, though. In classical physics, two or more observers can look at the same object and see the same result. However, if we follow quantum physics, a rock could be different velocities and in different positions to each and every observer. So, since this is happening multiple million times, trillion times a second, and it's decohering, the environment, say a person walks up to it, moves air particles, and the air particles knock into here. Well, now it's this, our red proton is now entangled with these air particles, and it is now changed. So that person, say he sees the electron is going 5,000 miles per second. Well, say another person decides he wants to measure it using a little speed sensor, and that speed sensor also moves particles around. Well, now it's entangled with different things, and its superposition is now different, so the person could see different things. So the two observers could see very different things if the world followed only classical rules. Each person would observe the world differently, which is not the case in regular physics. If two people were to look at a ball on the ground, they'd see the exact same ball on the ground, standing still at the exact same place. So, therefore, a Polish-American physicist named Wojciech Zurek argues that two things must be true in order for quantum physics to check out. 1. Quantum states must have states that are especially prominent and appearing, called pointer states. So, it seems I'm running out of space. So let's just go delete our quantum classical transitioning. So these pointer states are particular states that seem to appear very readily when being seen, which is part of the reason why we can get consistent answers for certain things. These states can be they're called pointer states, Zurich says, because these states can be encoded into the pointer of a measuring device. So, say there's a pointer state of mass, or not mass, mass is different, it's intrinsic value, but say position. We can measure this ball's position as xy. This is a pointer state because it can be encoded into a measuring device. Or say speed. If the ball is moving this way at 5 units, we can measure this ball's speed in a speedometer, and let's call this our little speedometer, and we record 5 units. So that's what he means by pointer states. So speed and position and the physical properties we know of are pointer states. And the rotations, Zurich argues that the notations of speed, position, direction, and so on only exist because these quantum pointer states exist. What's special is that these pointer states are not scrambled by the environment. So when, say, we go back to our super jumbled up, tangled up mess of different particles, photons, electrons, and protons all messing around with each other, for some reason these pointer states, they are not messed up by this collapse of the superposition. So when, say, this blue proton collapses right here, and it won't collapse into a really odd pointer state that we don't know of, that doesn't involve mass or doesn't involve speed. It'll collapse into one of those, and then in turn everything else collapses as well. So pointer states, for some reason, when they get collapsed, it seems that they can't be scrambled or randomly changed by other things affecting it. And the pointer state is preserved or collapsed into a near identical state or an exact state. So, say we go back over here, and what if this blue proton does make all these particles collapse into a state different from a pointer state? Well, if it's so similar to a pointer state that it's pretty much indistinguishable, it doesn't matter. So, position, for example, is an environment resilient state. This selection of Poynter states is described as environment-induced superselection by Zurich. This is where we get this natural selection part, the Darwinism part in quantum Darwinism. And the second thing that Zurich argues must be true for quantum Darwinism to check out is Poynter states must be able to create the most replicas in themselves from all of the other possible states. So when measuring an object, photons are scattered off an object. So let's take our ball here, and we're going to make some orange photons to scatter off this ball. Let me erase this real quick. There we go. So when measuring this ball, photons will scatter off this object. Some will go around, some will just pass right by and seem to just barely nick it. And we can see this ball because these photons are coming away from this ball and into the human eye. And that is how we see it. The human eye. Not a very good eye. That works. So, by replicas, I mean that these photons are changed. Their position and speed is changed by hitting the ball. And the reason the ball is there, its position is a Poynter state. So, lots of photons scattered off in a certain way need to exist in order for a bunch of people to see it. And position makes sure that a lot of photons get scattered off this ball. And in a sense, this ball is creating replicas of its presence in these photons. The photons are being changed by the ball. And something such as speed would create replicas of itself in the air molecules it pushes away. We would be able to sense the wind from a ball whizzing past us. So it essentially makes replicas of its existence in the air particles around it. So these things would be Poynter states, and position and velocity are Poynter states because they leave their replicas, traces of themselves all over the place. And all other possible positions that something can be in, or states that an object can be in, are called from this superposition because they don't create enough replicas for them to be detected by us. And that calling is what we call the calling of the fittest, such as like with regular Darwinism. Darwin theory says that the weakest animals are killed and the strongest genes survive. It's just like quantum states. The quantum states that can produce the most replicas survive, and the quantum states that don't make it into the classical physics world. And that is where quantum Darwinism is defined in. So, to clarify a few things, systems don't have to be under observation to be classical. That would be weird, because as long as the information is out there and could be read is what matters. Quantum and classical transformation existed long before we did, so there doesn't have to be a person watching the ball to know that for a quantum particles in the ball to collapse into classical particles of what we know as just the ball. We humans haven't been around for 4 billion years, so that just doesn't make sense to say that only observation causes quantum to turn into classical. So, quantum Darwinism challenges a hole/a myth in the quantum mechanics that the transition between quantum and the classical worlds cannot be explained by quantum theory. Quantum Darwinism is, in definition, the explanation of that theory, of this transition. So, let me get my notes straight. Recently, quantum Darwinism has been tested in the laboratory. This past year, 3 teams have tested the theory, the ones from China, Italy, and the last one, excuse me, let me look through my notes. The last one being from China, Italy, and Germany. So these three groups have tested quantum theory in the laboratory. So the three would be: one was led by Paternostro at the Sapienza University of Rome, and the other led by quantum information expert Jianwan Pei at the University of Science and Technology of China. These two did nearly identical experiments on photons in order to test quantum Darwinism. So let me get rid of some of this stuff here in order to create some space, and I can start my sketch of this theory, of these experiments. And there we have it. Open space now. So in both of these experiments, the experimenters used one singular photon of light. Let's make it golden yellow. One singular photon of light as the quantum system that they were testing on. And then they used a few other photons. Let's make it orange, as the environment that was affecting this singular quantum system of the photon that the researchers were looking at. So these photons, the orange ones, are the environment of the yellow photon. And both teams used lasers to manipulate the singular measured photon, and then recorded the information from the surrounding, now entangled photons, trying to search for the photon's polarization, a pointer state. So the polarization is essentially like its magnetic affinity. So is it positive or negative? Or not positive or negative, but does it have one polarity? Does it attract it, or is it repelled? So using little lasers, let's make these red, they shot this photon here and had it get entangled with other photons around it. So it would now be entangled with this photon, it'd now be entangled with this photon, it'd then be entangled with this photon and this photon. And then the researchers then looked at these photons here, the ones that it was entangled with, to see how they changed according to how this yellow photon here changed, and if they collapsed into similar polarities. So a key prediction of quantum Darwinism is the saturation effect. All info about a quantum system, i.e. our photon here, can be obtained by just a few surrounding particles or objects. So all the information about polarity we could get from just these four here that were entangled with it. And the teams found that measuring a single environment photon revealed a ton of info about the system's photon's polarization, and measured an increasingly larger set of environment photons led to diminishing returns. So if they measured just, say, this photon right here, let's erase all the rest. They measured, say, just this photon right here with the black arrow, they'd be able to figure out the system photon's polarity, because they were both entangled with each other, and this photon's entanglement changed based on this one's. So, but as the researchers increasingly used more and more photons, this photon here, this photon here, this photon here, that one here, 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 here. Let's add some more photons in for dramatic effect. All these photons, if they measured all these photons, they can't really learn anything more about the polarization. They already know that this photon and this photon are connected via in polarization. So all these photons, all the other ones other than this one right here, were really not necessary. There are diminishing returns as you continue measuring more and more. They just don't give you much more information. And that is saturation. That is the saturation effect. The more you measure, the less and less information you get from each measurement. Now, I've only talked about 2 experiments. The third experiment, led by quantum optical physicist Fedor Jelezko at the Ulan University in Germany, in collaboration with Zurich and others, used a completely different system and environment. They, instead of using a singular photon and a few photons around it, they used diamond as the environment, and a single nitrogen atom in the diamond as the system. So the nitrogen atom was embedded in the diamond as an impurity. It wasn't man-made, it was just there, and they identified that one nitrogen atom as the system. So nitrogen has one extra has one extra valence electron, so it couldn't pair up with the surrounding carbon atoms. And this extra carbon can be, excuse me, my notes were wrong. So this nitrogen could not pair up with the carbon, as all the carbons filled up their 8 valence electrons with surrounding carbon. So this carbon is carbon 12. However, within this diamond, there are other isotopes of carbon, such as carbon 13. Carbon 13 is a special state of carbon because it has one extra electron. So nitrogen and carbon 13 both together have one extra electron flying around, which gives them spin, because those electrons can't match with a different electron to negate each other's spin. So the nitrogen spin can interact with carbon isotope 13, which accounts for about 0.3% of the carbon atoms in the diamond. And the nitrogen atom is found to be strongly coupled with about 4 carbon 13 atoms in a 1 nanometer radius on average. So that would be the environment they'd test. So I haven't been drawing a picture, so let's start on my picture here. Alright, I will draw the little crystal lattice of diamond here, and let's make it turquoise. So this is the crystal structure of diamond, and these are all carbon 13 or carbon 12s. Let's put a little carbon 13 in here, and then go back to doing carbon 12s. And of course, since diamond is a crystal, it has very uniform structure. Drop another carbon 13 in there. Continue on with our carbon 12s. Another carbon 13. And then we continue with carbon 12s. Carbon 12s, carbon 12s, carbon 12s. Oh, and then this is where we hit our special nitrogen. And we continue with carbon 12s. And all of a sudden, there's a carbon 13 here. And carbon 12. So these carbon 13s are special because, as I said, they have an extra valence electron, and this nitrogen has an extra valence electron, meaning that since the electrons aren't paired up nicely like all these carbon 12s are, they have spin now, which is the exact spin as the electron. So the team, Zurich's team and others, they could use they could measure the spin of these atoms, and the nitrogen, and when they used radio waves and lasers to change the spins of, say, these carbon-13 atoms or the nitrogen atoms, they were able to test how the nitrogen changed about 4 other carbon-13 atom spins around it, since they were entangled with each other due to the radio waves that they were, the very fine-tuned radio waves they were using to change them, and the lasers they were launching through to change it. And within these tests, they observed redundancy characteristics. The nitrogen spin state was recorded in the carbon-13 atoms, just as the other way around works as well. The carbon-13 could record in the nitrogen, but nitrogen was the system here. They were testing the system, and carbon-13 being the environment. So these experiments are extremely rudimentary, however, and they only show what was expected, nothing new. The experiments also cannot be used as proof that quantum Darwinism explains the quantum classical shift, and they cannot cleanly rule out all other explanations for the emergence of classicality. So this is not all end-all, be-all information that they've gotten, but it is a start. So researchers of quantum Darwinism have also tried to develop quantum Darwinism into a framework that doesn't see the world as a system and the system's environment, because the system's environment consists of other quantum systems. So if we were to say this here nitrogen atom is our system, and everything else here, all these carbon-12s, all these carbon-13s are the environment, that is incorrect, because this carbon-13 is its own system as well. It can change this carbon-13, it can change this carbon-13, it can change this nitrogen, just as well as this nitrogen can change everything else as well. So it is not good to separate it into simply just environment and system, because in reality the way the real quantum mechanics works is that it's just a bunch of systems interacting with each other rather than a system and an environment. So QD, quantum Darwinism, is still in its infancy, and really the best way to figure out more about measurement in the quantum sense is to simply make better measurement tools for measuring. And until then, we are currently contained by what we can measure in the lab, so we can't figure out more about about quantum Darwinism, due to the fact that we're contained by these measurement tools, since atoms and electrons are so small. So my questions after completing this article are many, mostly have to do with quantum mechanics in and of himself, but one of the questions I have is how particles are when they're entangled with each other, and when they collapse, what causes this collapse? Because when particles, say over here, they hit each other, they're hitting each other, yes, they're getting collapsed, but when does the first one collapse? When does the first one begin to change? Because as we know, it's not just observation that does it, because humans haven't been around forever, so obviously these have been collapsing a long time since before humans have been around. So what first causes this collapse every 10 to the negative 31 seconds? Which is just really confusing me. And then also another question I have is about these electrons, like the pointer states. What happens in the event that, I know it seems very improbabilistic because pointer states are super high probability that the pointer states are what a object collapses into. But since quantum physics is all probability, as I've read, what happens in the extremely low improbable chance that an object, a large system object like in the classical physics world, actually collapses into one of the very improbable non-pointer states? So would we end up seeing something we don't understand, like a new physical property, like position or time or mass, but something we've never seen before? And I think that would be the two most burning questions I have about this. So I'll be cutting it out. Thank you.